Hey, hello again. Good afternoon, everyone. We're now going to start the second conference today. It's a conference on gases, which corresponds to chapter 11 in our course. I would say the most effective way to learn gases, at least at the Chem 65 level, is to do it in reverse chronological order. So typically a textbook will give you the individual ideal gas equations, and then it will go back and combine them together into the ideal gas equation. We're going to do the opposite. We're going to look at the ideal gas equation and then break it up. So the ideal gas equation is PV nRT, where P is pressure, V is volume, N is moles, R is called the ideal gas constant, which is just a numerical constant, and T is temperature. Uniquely temperature in Kelvin, not temperature in Celsius or Fahrenheit. It has to be temperature in Kelvin. If we divide both sides of this by NT, then that NT cancels, and we're left with PV over NT equals R. We're actually going to be interested in this form of the ideal gas equation, this representation, and I'm actually going to draw this 4 times after we've erased the board. So we can do it one at a time. So let's plot. We said that PV over NT is R. So if we look at 2 variables, so we have 4 variables total are equal to a constant. Let's look at 2 of those variables initially. Let's look at P and V. Okay. And I'm going to fix N and T. What does that mean? Well, if I'm looking at 2 of the 4 variables, I have to keep the other 2 fixed, so that means they don't change. So I'm going to keep the moles fixed, so no molecules go in or out, and I'm keeping a fixed temperature by the aid of a water bath or something. So anything that's fixed, I can ignore. So we're saying that PV is a constant. Let's replace R with just the word constant. Okay. So PV is a constant. Now, what's the relationship between P and V? Well, if I take the V to the other side, this means that if the V is a product on the left, it will be a quotient on the right, so it will be a denominator on the right. So P is proportional to 1 over V. That's an important relationship. What does that mean? That means as pressure increases, volume decreases. This makes sense. Consider a balloon. You take a balloon and you try and decrease the volume, you try and compress the volume, you increase the pressure inside the balloon. So if you squeeze a balloon, it will squeeze out somewhere else. It will try and expand its own volume. What does the graph look like? The graph would look like this. As pressure is large, volume is small. Looking over here, if volume is large, the pressure is small. So this is an indirect or an inverse relationship. If we look now, instead of, if pressure is proportional to 1 over V, why don't we just plot pressure against 1 over V? So instead of volume, let's look at 1 over volume. If we did that, we'd get a nice straight line, which follows the straight line equation. So y equals mx plus b. That's the equation for a straight line. Remember that y in this case would be the y-axis, or pressure. X would be the x-axis, or 1 over volume. And b is the intercept. In this case, ideally, it would be 0. Because if you have 0 volume, you have 0 pressure. This is known as Boyle's law. After Henry Boyle in the late 1600s, early 1700s. Okay. So this is one of the 4 equations we're going to look at. Go back again to our PV over NT equals R. We've already looked at P and V. Let's look at V and T. If I'm looking at V and T, I'll need to fix P and N. So pressure is constant, moles are constant. If they're constant, we can ignore them. And we just replace this with the word constant. So V over T is a constant. Remember, T is in Kelvin. If we bring T over to the other side, if it's a denominator on the left, it will be a numerator on the right. We know that V is proportional to T. So it's a direct relationship. A direct relationship we know is a straight line. The y is mx plus b equation. It would intercept at 0 Kelvin because the temperature must be in Kelvin. But we can always plot this in terms of Celsius. We can't do calculations in Celsius, but we can always plot a graph in Celsius. We would still get a straight line. But instead of 0 Kelvin, it would give us negative 273 Celsius. So this is where the relationship Kelvin equals Celsius plus 273 came from. One of the origins. So this 273 is if we take 273 to the other side, Kelvin is negative 273, or 0 Kelvin is negative 273 Celsius. This is known as Charles's law. Or Charles' law. It's a French Charles, rather, like Charles de Gaulle Airport. That type of Charles. Okay. Notice Boyle's law and Charles' law both come from the ideal gas equation. Okay. Halfway there are 2 more equations. PV over NT equals R. Again, that's our ideal gas equation. Let's look at pressure and temperature. That means we're going to fix volume and moles. So we don't allow this thing to change volume. We have hard walls, a hard exterior, maybe a steel canister, and we don't allow anything in or out, so the moles are fixed. If we are fixing V and N, we can ignore it. Remember, R is just a constant. In analogy to Charles's law, we know that pressure must be proportional to temperature. That's going to give us a straight line. Y is mx plus b. If we're looking at Kelvin. Likewise, although the calculations must be in Kelvin, we can plot the graph in whatever units we choose. If we plot this in Celsius, it would again give us negative 273 Celsius. But it's a straight line equation. This is known after two people, Gay and Lussac. So it's called the Gay-Lussac law. One more. PV over NT is R. If we put moles against volume, so therefore we're fixing pressure and temperature. If we're fixing pressure and temperature, we can ignore them. If we take the n to the other side, if we transpose the n to the other side of the equal sign, we know that volume of a gas is proportional to the moles. This is quite obvious. If you have more gas, its volume will increase. That makes sense. It's a direct relationship. It's also a y is mx plus b equation, which is a straight line equation. And this is known as Avogadro's law. It's the same Avogadro as Avogadro's number. In fact, historically, this was part of the push towards identifying the concept of Avogadro's number. The components, not the whole story. Okay, so we've seen 4 equations so far. Let's summarize those 4 equations. So far, we've seen pressure times by volume is a constant. We've seen volume over temperature is a constant. We've seen pressure over temperature is a constant. And finally, we saw volume over moles is a constant. So we saw Boyle's law. Right here, Boyle, Charles, Gay-Lussac, Avogadro. So those are 4 laws that we saw. Remember, they all came from the ideal gas equation. So historically, these were discovered, and then it was noticed how they could combine together. You notice pressure is always a numerator where it's found. So pressure is always a numerator. You'll notice that wherever it's located, volume is also a numerator. And wherever it's located, temperature is always a denominator. And the one occasion where it's found, moles is a denominator. And it was found that this was always a constant. So historically, it went that way. But when you're learning it, I recommend you go that way. So in short, this is the only thing you have to memorize, because they're all the same thing. We know that constants don't change with time. So a constant is a constant because it doesn't change with time. So that means initially PV over NT equals R, It also means that finally PV over NT equals R. If R is a true constant, it won't change with time. So initially it's true, finally it's true. Under initial conditions, we know that PV over NT equals R. Well, that R is the same R here. So that PV over NT must equal that PV over NT. So that's confusing. So now we need to label the initial and final. For some reason, they chose the numbers 1 and 2. So we represent the initial conditions with the subscript 1. We represent the final conditions with the subscript 2. So P1 V1 over N1 T1 equals P2 V2 over N2 T2. Now, this is a combination of all the gas equations. Let's say moles don't change. If the moles don't change, if your sample, let's say you just put some gas in a container and nothing comes in, nothing goes out, it's a fixed amount of sample. Okay. Let's say it's a fixed amount of sample. Then N1 equals N2. Well, that just becomes a constant then, and we can ignore constants. If N1 equals N2, it implies that P1 V1 over T1 is P2 V2 over T2. This is not new, it's just a combination of the above with a fixed sample size. But it's given a new name. It's called the combined gas law. So far we've got Boyle's law, Charles' law, Gay-Lussac law, Avogadro's law. Combine them together, we have the combined gas law, that's 5. They all came from the ideal gas equation, 6. So there's going to be 6 equations, but we're smart enough to realize that it's really just one equation, and it's really just that equation. Let's consider units of pressure. Well, there are many units of pressure. The ones that you will be accountable for are the following. You'll have to base everything on 1 atmospheric pressure. So ATM is short for atmospheric pressure, and that's roughly the pressure of our atmosphere at sea level on this planet. I'll need you to know that that equals 760 millimeters of mercury, and that equals 760 torr. So they're the units I'll expect you to know in Chem 65. Okay, 1 atmospheric pressure is 760 millimeters of mercury, is 760 torr. Let's plug some numbers in and see if we can do a quick couple of calculations. So just off to the side here, I have the textbook. I'm just going to pick a number of questions to solve on the board. Just to represent how straightforward this could be. Okay, so I have one here. So here's all the variables that we might need, and we're given some. We have to solve for others. Let's just try a couple of these. So let's say that's 1.21 atmosphere. V1 is 1.58 liter. P1 is 12.2 degrees Celsius. I'm really putting it close together, aren't I? P1, B1, T1, P2, B2, T2. So 1.21 ATM, 1.58 liter, 12.2 degrees Celsius, 1.54 ATM, question mark, 32.3 degrees Celsius. Okay, so we're given some information. We're not given all the information. We have to solve for V2. Whenever you're given, in the question, whenever you're given initial and final values, always start with the combined equation. So you would recall the combined gas equation. You have to isolate V2, so we have to get rid of P2 and T2. You'll know from your mathematics, if you want to cross multiply a numerator, it becomes a denominator on the other side. And if you want to transpose a denominator, it becomes a numerator. So the P2 goes down, the T2 goes up. So we would have V2 is P1, V1, T2 over T1, P2. Again, the P2 has gone down, and now it's down here. The T2 has gone up, and now it's up here. So I've now cross-multiplied my equation to solve for V2. So V2 is just P1, which is 1.21 atmosphere. We're just going to use basic algebra now, no need for dimensional analysis. V1 is 1.58 liter. T2, remember, you can only use Kelvin in the calculations. So remember to add 273 to this number to get Kelvin. So I'm going to add that on my calculator. So 2.3 plus 273. So this is 305.3 Kelvin. So again, it must be in Kelvin. Not too worried about sig figs at this point. T1 is 12.2, so that's 12.2 plus 273, which is 285.2 Kelvin. And finally, P2 is 1.54 ATM. Let's look at the units. Kelvin cancels Kelvin. Atmosphere cancels atmosphere. And I'm going to have volume in units of liter. Let's round the final answer to 2 sig figs to match our lowest, actually 3 sig figs, right? 1.21. So we're going to round to 3 sig figs. So 1.21 multiplied by 1.58 multiplied by 305.3 divided by 285.2 divided by 1.54. Round into 3 sig figs. So V2 equals 1.33 liter. Critique your answer. Does this make sense? Well, to go from P1 to P2, the pressure increased. Remember, the pressure is proportional to 1 over volume. Remember Boyle's law. Pressure is proportional to 1 over volume. P1 to P2, the pressure went up. If the pressure goes up, the volume has to go down. Indeed, V2 is less than V1, so the volume did indeed go down. So always remember to critique your answer using the basic proportionalities of each individual equation. We'll have maybe another question with a unit conversion built in. What have you given a couple of different units? What have you given 721 for? 1.4, 141 milliliter, 135 Kelvin. Let's say this is 1.35 atmosphere. But let's just double check. Let's say it's 2.35 atmosphere. Okay. V2. I'd have to. I'm trying to convert all to atmosphere in my head, and I can't do it. So give me 1 second. Because if I don't do it right, then the numbers won't make sense. So I need. Okay. This is actually 1.05 atmosphere. 1.054. Okay. And then finally, 152 mil. And that's our question mark. Okay, so this is the last basic example we'll do. You would then go on and try some homework questions or look at the PowerPoint. I see initial and final conditions. So I write down my ideal gas equation correctly, ideally. Okay. I need to solve for T2. So I need to bring T2 up here and take everything else to the other side. So I've got T2 goes up here, P1, V1 comes down over here. T1 would go up here and join P2, V2. So I've isolated the variable I want. Remember, this must be in Kelvin. Okay, so T2 is P2, which is 1.054 atmosphere. V2, which is 152 mil. There's no need to put this in liter. Not yet, anyway. T1 must be in Kelvin, and it is. P1 is in torr. Now there's a problem. If I use that number as given, my units won't cancel. Atmospheres and torrs won't cancel. So I need to convert torr to atmospheres. So 721 torr. And I use my conversion. An atmosphere is 760 torr. So I use my little bit of dimensional analysis here. Convert to atmosphere, which then will cancel here. V1 is mil. Again, so long as your units make sense, you don't have to put it in any specific unit other than temperature must be in Kelvin. So I'm going to get temperature in units of Kelvin. Okay. So let's see. 4, 8, 7. Okay. 1.054 by 152 by 135 divided by equals divided by 141. Okay, so rounded to 3 sig figs, this should be 162 Kelvin. Does this make sense? Well, let's look at P and T. The pressure, let's see. 721 torr is less than 760, so this is less than 1 atmospheric pressure. So less than 1 atmospheric pressure, greater than 1 atmospheric pressure, so the pressure increased. We know the pressure is proportional to temperature. Gay-Lussac's law. The pressure increased, the temperature must have increased. So we predict T2 must be bigger than T1, and indeed, our T2 is larger than T1. If we found something else, we would know that we've mislabeled, and this is the most common mistake that students make. They mislabel 1s and 2s somehow, and they get an answer that doesn't make sense. The ones that check their answer catch the mistake, and the ones that don't check their answer have no idea until I show them their exam. So always critique your answer, knowing the relationships that you know. Okay, so we started a few minutes late. I'm just going to look how long we're into our conference. I have no idea, so I'm just going to keep going. Okay. Let's do a couple of questions using the ideal gas law. Okay. So again, I'm going to the course text. I'm just going to pick a question out the back of the book. Okay. So I'm just picking a question at random. What's the volume of 0.255 mole of hydrogen gas? Beg your pardon, helium gas. Helium gas at 1.25 atmosphere and 305 Kelvin. Okay, so it's a random question out the back of the course text. Typical exam style question. What's the volume? Okay, how would you know this is an ideal gas law type question? Notice there's no initial and final conditions. You just ask for a snapshot. What's this value at this instant in time? You have a volume, V, moles, N, temperature, T, pressure, P. I provide R, so you always have R given to you. So the variables lead you to the ideal gas law. You've got PV is nRT, that's the ideal gas law. And you need to solve for V. So volume is nRT over P. Now we just simply plug the numbers in. So volume is moles, which is 0.255. Again, we can just use some algebra. R, I will provide, you don't have to memorize it. It's 0.08206. It's got 4 units. Liter, atmosphere, per mole, per Kelvin. Temperature is Kelvin. And then we divide all of that by pressure, 1.25 atmospheres. Previously, we said it doesn't matter if your volume is in liter or milliliter, but that's because we didn't use R. Notice that R has liter and atmosphere in it. All your volumes, if you use R, must be liter. all of your pressures must be atmospheres. Otherwise, they won't agree with the units here. Kelvin cancels Kelvin. Mole cancels mole. Atmosphere cancels atmosphere. The only unit that won't cancel is liter, so we're going to have volume in liters. So we'll do the basic algebraic equation. 0.255, 5.08206 by 305 divided by 1.25. We'll round the answer to 3 sig figs, and we get 5.11 liter is our final answer. So again, if you have initial and final conditions, you would look to use the ideal gas equation. Incidentally, if you use the ideal gas equation and the question doesn't specify a variable, assume that it doesn't change. Anything that's not specified, ignore. If you don't have initial and final conditions, you can just go ahead and use the ideal gas law. So to summarize so far, if you're given initial and final conditions, use the combined gas law, which is P1 V1 over T1 is P2 V2 over T2. Otherwise, oh, actually, before we do that, if, well, cancel any variables that don't change or aren't given. So for example, let's say you're given initial and final conditions. So you immediately write this down. Let's say you're told that the temperature is constant. If the temperature is constant, ignore temperature. So this then becomes a Boyle's law question. Let's say you're told that the pressure is constant. Ignore pressure. This then becomes a Charles law question. If you're told the volume is fixed, ignore volume. This becomes a Gay-Lussac question, etc. for Avogadro's law. So again, it's all contained within the combined gas law. Otherwise, use PV is nRT. You've really only got two options. Okay. I think we have some time, maybe 10 or 15 minutes. Sometimes I'll derive the ideal equation for you. I don't necessarily think we need that this time around. So if anyone has any questions, now would be a good time to ask. I'll wait a couple of seconds, see if anyone has a question. Okay, then we'll wrap up real quick by briefly looking at the kinetic molecular theory of gases. Okay, so we'll look at the kinetic molecular theory of gases. What does theory mean? Theory means based on experiment. So we have experimental evidence. Gases means gases. Molecular means molecules. So that must mean gas molecules. Kinetic means motion. So the kinetic molecular theory, or KMT, you might hear people say KMT. What does KMT do? It explains how, based on experiment, gases move. We're going to look at how gases move. So gases move incessantly. What does incessant mean? It means doesn't cease. It means doesn't stop. So always moving. And there's a caveat. The caveat is assuming the temperature is greater than 0 Kelvin. So we'll see in a few minutes that we have to make some assumptions that we haven't spelled out yet. But when we say incessant motion, we're assuming that there's temperature. Okay, so incessant motion, haphazard, random motion. So you cannot predict. So you could never be a catcher trying to catch a gas, because you could never predict where it's going to be. It's haphazard. Elastic motion. What does elastic mean? Elastic means doesn't lose energy. Which is very unusual. Gases don't lose energy, assuming that we don't change the temperature. Let's put a double asterisk here. Change in temperature. So here we're saying that temperature must be greater than 0. Here we're saying that the temperature, the change in temperature is 0. Or in other words, there is no change in temperature. Okay. We're going to go back and we're going to erase this and we'll draw a diagram what this might look like. So let's say that this represents a room. And let's say you have a gas molecule in one corner of the room. And let's say it's a perfume molecule. So somebody sprays a molecule of perfume, and there's somebody over here would like to smell that perfume. And you spray it, you point it towards the person here, and you hold it and you spray it. If your aim's not perfect, and the gas, let's say there's no other obstacles in here, so there's no other gases here to collide with, it will move in a straight line until it hits something, but then you don't know where it's going to go next. It's unpredictable. It might go immediately back, and then it might decide to go over here. Why? Because it's going to interact with the atoms. This quantum material here will interact with the quantum atoms in the container. It might go here, and then it might go here, and you just never know where it's going to go. And if you're lucky, it might go right up your nose. The point is it's random, straight line motion. There are no curves here. That's just my poor drawing. But it's perfectly straight line motion until it hits something. And when it hits something, you don't know in which direction it's going to change. It doesn't lose any energy, though. So the energy it had here and the energy it has here are the same. Elastic motion. It doesn't lose energy when it hits something. This is unusual. Consider a gas and a basketball. Over time, if we look at the energy of a basketball, if a basketball is dropped from a certain height, the basketball will hit the floor, it will bounce, it will lose some energy. It will bounce again. Why is it moving forward? Because time is going on. Time is pulling it forward. Lose some energy, and eventually that basketball is going to sit on the floor. That would be inelastic motion. So the final energy is going to be less than the initial energy, or the change in energy is not equal to 0. Okay. Gas, on the other hand, according to KMT, we look at energy against time. This gas molecule never loses energy, never gains energy, never loses energy forever. This is elastic. The final energy value equals the initial, or the change in energy is 0. That's unusual. It makes sense when you think about it, though. In the parking lot, our vehicles are parked, hopefully with some gas molecules in the tires. That, we inflate our tires with gas. The pressure of the gas in the tires in the morning, we hope, is the same, not more, not less, but the same as the pressure in the tires when we're ready to drive home. If gas molecules did this, the gas would condense into a solid, and we'd have a little pool of gaseous, of solid air in our tires, and the tires would deflate. The fact that pressure exists as something that will persist over time is testament to the fact that gas molecules undergo elastic collisions when they move, or elastic motion. So when you think about it, this makes sense, although it's unusual because we live in a world where basketballs do this. Okay, I think we've got about 10 minutes left, but we're almost done. The last thing I'd like to look at is just temperature. So temperature is related to kinetic energy. Kinetic energy, I think we've looked at already in our course, is mass times by square velocity over 2. So the energy of motion, kinetic energy, is the mass of an object, its square velocity over 2. So the mass of a gas molecule is just its mass in grams per mole multiplied by its velocity squared over the number 2. If we take on average, if we just average all the molecules in a room, if we take the average velocity, then we get the average kinetic energy. Well, when we look on the average, this is proportional to the average Kelvin temperature. So the energy that we've been talking about, the kinetic energy, on average, is proportional to Kelvin temperature. Notice it's Kelvin and nothing else. This is one of the reasons why we have to use Kelvin temperature in gas calculations. This is why in the previous caveat, the asterisks, we said that temperature must be greater than 0. Because if temperature is 0, there's no energy. And then you can't talk about kinetic molecular theory because there is no motion. So the motion, or the theory by definition, assumes that you have motion. Otherwise, it's not a motion theory. Okay, so this is important. I would expect that you know this in my Chem 65 class. Use this and refer to this in your exams. Okay, we're almost done. If there are anybody with questions, I'll take them now. Otherwise, we'll wrap this thing up. Okay, I don't see any questions. So slightly ahead of time, we'll wrap this conference up. So stay tuned for further announcements about forthcoming conferences.